Okay, this is the last lesson for your topic on chemical bonding. Alright, and we are going to look at a type of bonding called metallic bonding. Now, at this point, some of y'all may recall, sure, didn't you say that metals don't combine with metals? Alright, back at the very early lessons, I mentioned that a metal can combine with a non-metal can combine with a non-metal, but metals they tend to give away electrons. So when a metal meets another metal, both only wants to give electrons. So they cannot combine. That is correct. So a metal cannot combine with a metal. Then where on earth do we get metallic bonding? If we look at a metal element itself, if you look at your silver, your copper, your iron, what is holding the atoms together? Alright, it's actually your metallic bonding. Alright, so within a metal itself, there's actually some kind of bonding which is called your metallic bonding. Before we go into that, let's do a very quick recap. So we have learned two kinds of bonding before metallic bonding: ionic and covalent. Ionic bonding occurs between a metal and a non-metal. Alright, so when you transfer electrons, the metal becomes positively charged, the non-metal becomes negatively charged, and plus and minus, this kind of attraction is called electrostatic forces of attraction. So this is your ionic bond. Ionic compounds have a giant ionic lattice structure. Okay, where as the name suggests, there are many ions in there, and it has a regular and repeating pattern of plus and minus, plus and minus. Alright, because of the structure, it has the following properties. It has a high melting point, boiling point. Okay, it is soluble in water, insoluble in organic solvents, and it for electrical conductivity in solid state, it cannot conduct electricity, but when aqueous or molten, it can conduct electricity. Okay, this is just a recap. If you cannot remember why is it so, or cannot recall the explanation, please go back and review the previous lessons. For covalent compounds, or covalent substances are formed when a non-metal combines with another non-metal. How do they combine? They combine by sharing electrons. Okay, so when they share electrons, there's again some form of electrostatic attraction between the protons in the nucleus and the shared pair of electrons. We call this a covalent bond. Okay, so there are two kinds of structures for covalent substances. You can either have simple molecular structure, or you can have giant molecular structure. Okay, for giant molecular structure, there are only three compounds that we need to remember, three substances that we need to remember that has giant molecular structure: your sand, your diamond, and then your graphite. Okay, so because of the way of the atoms are being arranged in your simple molecular structures, your giant molecular structure, they have different properties. If you can recall, for simple molecular structures, the molecules they attract one another weakly with weak intermolecular forces of attraction. So as a result, it has low melting point, boiling point. Okay, it is insoluble in water but soluble in organic solvents. Okay, and since there are no free mobile ions or electrons, it cannot conduct electricity in any state. But we need to take note of certain substances that can react with water to form ions in solution. Okay, for giant molecular structures, for compounds or substances with giant molecular structures, in order to melt or boil them, we need to break the many strong covalent bonds. So as a result, it has a high melting point and boiling point. Okay, it's insoluble in all solvents. And for electrical conductivity, in general, for diamond and graphite, for diamond and sand, it doesn't conduct in any state. Okay, but for graphite, it can actually conduct electricity. Okay, due to the unique bonding type in graphite, where each carbon atom actually has one electron that's left over, and this electron is free to move. So now we'll look at metallic bonding, the same three categories: how is it formed, what it is, and the structure of metallic substances. Now, how is metallic bond formed? It is not formed, it simply exists in all metals. Okay, what it is, I'll come back to it after I describe the structure of a metal. Now, at this point, I will want you to recall any metals that you're familiar with in daily life, and most students will be able to tell me things like iron, copper, silver. Alright, now if you think about them, at room temperature pressure, these metals exist as solids. Okay, so if I were to zoom into a piece of iron, for example, how would the atoms be arranged in the solid state? Okay, again, tapping on your kinetic particle theory, you would expect that the atoms are closely packed, very closely packed, alright, in an ordered arrangement. Alright, so this is exactly what you will see if you zoom into, for example, a piece of sodium metal. Okay, now sodium has the proton number 11. Alright, so if you can again recall, in atomic structure we learned that it has the electronic configuration 281, which makes it unstable because it doesn't have a fully filled valence shell. So sodium actually has a high tendency to lose its valence electrons in order to become stable. Same for any metals. Alright, any metal would have 1, 2, or 3 valence electrons in the outermost shell, so it has a high tendency to lose these electrons in order to become stable. So what actually happens in a giant metallic structure is this, that the valence electron will actually come out of the atoms. Alright, so the valence electrons will actually come out, and these valence electrons can move around freely in the structure. So we actually call this structure a giant metallic structure. Okay, once again, why giant? Because whatever I've just drawn only represents a section of the real structure. It extends again indefinitely in all directions. So there are many sodium atoms which will form sodium ions and many electrons in the structure. So we call it giant structure. Metallic because it is made up of metal atoms. And then once again, if we look at the structure, there's something that's positively charged and there's something that's negatively charged. So there's some kind of attraction, right? There's some kind of attraction between the metal cations and the electrons. Okay, how do we describe this? We describe this as strong electrostatic. Once again, it's between a plus and a minus, so we call it electrostatic. Strong electrostatic forces of attraction between the metal cations, because after the metal atoms lose their valence electrons, they become metal cations, and the sea of delocalized electrons. Okay, remember the electrons can move, alright, they move freely throughout the structure, so we call it sea of delocalized electrons. Now, one very useful way to visualize this structure is to imagine these electrons as glue. Alright, so these electrons are acting as glue to hold the entire structure together, to hold each metal cation in place, to prevent it from breaking down. Alright, so I've already mentioned what is it. What is a metallic bond? It is actually your strong electrostatic forces of attraction between metal cations and sea of delocalized electrons. So now that we have looked at the structure and bonding in metals, let's see whether we can apply it to predict the properties of metals. Again, the three properties that we're interested in is melting point, boiling point, solubility, electrical conductivity. Okay, as mentioned in the previous slide, your metals are all solids at room temperature, so they have high melting points and boiling points. Okay, in fact, we can easily explain for them if you can recall there is strong electrostatic forces of attraction between the metal cations and sea of delocalized electrons. So since the attraction is strong, in order to melt a metal, we need to move the cations or the metal atoms further apart, and they are held very strongly by the electrons, which is the glue. Alright, so a lot of energy is required to separate them. It has a high melting point, boiling point. Now, metals in general, they are insoluble in water, but we generally don't talk about solubility of metals in water because there are some metals that can react with water, alright, which we will learn in the chapter of metals later. Now, for electrical conductivity, let us try to recall the two conditions for a substance to conduct electricity and see whether metals fulfills the two conditions. So the two conditions once again are the substance must contain charged particles, that means something that's plus or minus, and two, the charged particles must be able to move freely. Okay, so if we look at the structure of metals, does it contain something that's plus or minus? Answer is yes. In the structure of metals, we have positively charged metal cations, okay, and then also we have the sea of delocalized electrons. So yes, it does contain something that's plus and minus. So condition number 2, can the charged particles move? Answer is yes and no. Alright, why yes and no? In a solid, remember your metal cations, they are actually fixed. Alright, they are held in fixed positions, so your metal cations are not able to move. However, your sea of delocalized electrons, as mentioned, they are actually just swimming around in the structure, alright, acting as glue. Alright, so these electrons, they are actually mobile. Okay, so condition 2 is actually met because there's something charged that can move in your metals. Alright, so based on that, it can conduct in any state actually. Alright, so when you see an unknown substance that can conduct in any state, it has to be metals. Alright, because metals is the only one that can conduct in solid, liquid and gas. Other than graphite, it must be a metal. So here are the frequently asked questions for metals. Why do metals have high melting point, boiling point? Why do they exist as solids? Again, it will be good to mention the structure, giant metallic structure, and then a lot of energy is required to overcome the strong electrostatic forces of attraction between your metal cations and sea of delocalized electrons. Alright, now if you haven't realized any kind of bonding in chemistry, they are all electrostatic in nature, meaning between something that's plus and minus. right? All kinds of bonds in chemistry are electrostatic in nature. So it makes it very important for us to highlight what is the forces of attraction between. Okay, for metals is between metal cations and sea of delocalized electrons. For ions, for ionic compounds is between your oppositely charged ions. For your intermolecular forces is between the molecules. Okay, so you have to get this right also. Now, why do metals conduct electricity? Because there is a sea of delocalized electrons which are mobile and can carry electrical charge. Okay, bear in mind again that in a metal, it is not the metal cations that are moving to conduct charge. It is the sea of delocalized electrons. Okay, and lastly, another property of metal is that it's malleable and ductile. What is malleable? What is ductile? Ductile means it can be drawn into wires. Okay, so for example, if I were to pull a piece of metal with sufficient strength, will it break? Answer is no. It will just become longer. Alright, so this property is called ductile. What is malleable? Malleable means it can be hammered into different shapes. Alright, so when if I hit a piece of metal with a lot of force, it doesn't break, but it will just bend. It will be bent into a shape. So why are metals malleable and ductile? Is because of the visualization of the delocalized electrons as glue. Alright, so when you apply a force and your metal atoms or your metal cations are displaced, the glue is still surrounding it, causing it to the structure to stay together. So how do we explain that? We say that the metallic bonding is not disrupted. Now the best way to illustrate this is to show the opposite of malleable. Right, the opposite of malleable is brittle. And a classic example of something that's brittle would be your ionic compounds. Okay, ionic crystals. Now imagine if I have a very large sodium chloride crystal and I hammer it with a large enough force. What will happen to it? Will it dent? Answer is no, it will simply break apart. Alright, this is what we mean by brittle. Now why is that so? Let's take a look at the structure of an ionic compound. Okay, it looks something like this. Plus minus plus minus. Alright. Now what happens if I were to apply a force and in doing so displace the top layer of ions one ion to the right? This is what will happen. I will end up with a structure looking like this. Okay, what you're supposed to take note in this structure now is that now the like charges are aligned. Plus is aligned with plus, minus is aligned with minus. So if you can recall, like charges, they repel. So what happens to the structure? The structure simply breaks apart at this point. So that this is why ionic compounds are brittle. So why are metals malleable then? Okay, again, we need to look at the structure of metals. We have positive cations. And then we have, and it is held together by the sea of delocalized electrons, which is acting as glue. Now if again I were to apply a force causing the top layer of atoms to move one atom to the right, now what will happen to the structure? We will get something like this. Now will this structure break apart? The answer is no. Why? Because the sea of delocalized electrons are still surrounding the metal cations. Regardless of where it's located, it's still surrounded by your sea of delocalized electrons. It's still surrounded by your glue holding the structure together. So that is why the shape will change, but the structure will not simply break down. And once again, how do we explain for that? Is that the metallic bonding is not disrupted. Okay, therefore metals are not brittle, they are malleable. Okay, so that brings us to the end of chemical bonding. We have looked at three types of bonding: ionic bonding, covalent bonding, and metallic bonding. So it's important to know what they are, how are they formed, alright, and how do we represent the compounds. And in the later part, we learn the structure, which will allow us to account for the properties of these compounds.